Every culture has dreamed of going back in time to fix a mistake, to change a tragedy, to see what once was. But here is the unsettling truth hidden inside modern physics. The universe is not neutral about this desire. It does not merely make time travel to the past difficult, it actively resists it. You can race into the future using speed and gravity, and the universe barely notices. But the moment you try to turn around and walk backward through time, reality itself seems to push back. The equations begin to shake. Energy explodes, space-time destabilizes. It's almost as if the universe is saying, you may look back, but you may not touch. When physicists say that time is flexible, they are not speaking poetically, they mean it in the most literal sense possible. Time stretches when you move fast. It slows down near massive objects. It flows at different rates for different observers. This discovery shattered centuries of intuition because it revealed that time is not a universal background ticking away the same for everyone. It is part of the fabric of the universe itself. Space and time are woven together, and when one bends, the other responds. This is why time travel, at least in one direction, emerges naturally from the laws of physics. The universe is perfectly comfortable with time behaving differently depending on motion and gravity. But buried inside this flexibility is something deeply asymmetric. The equations allow time to slow, stretch, and dilate. Yet they treat the two directions of time very differently. Moving forward through time fits neatly into the structure of reality. Moving backward does not. The future is a region of possibility. It has not yet been filled with detail. It is statistically open, probabilistic, and receptive to change. The past, on the other hand, is densely packed with information. Every interaction that has ever occurred has left a trace. Every particle carries a memory of previous events encoded in its state. The past is not just earlier time, it is a completed record. This distinction matters enormously. When you move into the future by traveling close to the speed of light or by sitting near a powerful gravitational field, you are not violating anything fundamental. Causes still come before effects. Information still flows in one direction. Entropy still increases. From the universe's perspective, nothing dangerous is happening. You're simply experiencing less time than everything else. The cosmic bookkeeping remains intact. This is why time travel to the future is not controversial in physics. It fits the rules cleanly and quietly. The moment you reverse direction, however, the tone of the universe changes. Backward time travel threatens to place effects before causes. It allows information to appear without origin. It opens the door to self-contradictory histories. Physics is not allergic to strange ideas, but it is deeply intolerant of inconsistency. The laws of nature are built on the assumption that the universe makes sense from one moment to the next. Once that assumption is violated, prediction collapses, and without prediction, physics itself ceases to function. This is why the future seems to cooperate while the past fights back. When you head toward the future, you are adding information to the universe. You are participating in the natural growth of complexity. When you attempt to go backward, you are threatening to remove or rewrite information that already exists. That is a very different operation. It is like trying to erase a book that has already been printed, distributed, translated, and archived across countless libraries. The universe resists this not emotionally, but mechanically. Entropy plays a central role here. The arrow of time, as we experience it, is tied to the tendency of systems to move from order to disorder. The future aligns with this flow. The past does not. To move backward in time would require reversing this flow on a vast scale, not just locally, but globally. Every particle, every field, every interaction would have to cooperate in undoing what has already been done. Physics allows local reversals in tiny systems, but not universal rewinds. The resistance grows exponentially with scale. This explains why the universe feels permissive in one direction and hostile in the other. It is not a moral judgment. It is a structural one. The future is underdetermined. The past is overdetermined. The equations reflect this difference with ruthless clarity. They allow time to slow, pause, and stretch forward, But when backward motion threatens causality, instability erupts. The most fascinating aspect of this is that the universe does not need to forbid backward time travel explicitly. It does not pose signs or draw lines in the sand. Instead, it lets the consequences speak for themselves. As soon as a physical system begins to resemble a pathway into the past, quantum fluctuations intensify, energy densities rise. Space-time becomes unstable. The environment turns hostile not because someone programmed it to, but because the structure of reality cannot support contradiction. What we are seeing then is not a limitation of imagination, but a revelation about how deeply ordered the universe is. Time is flexible, but not careless. It can bend without breaking, but it will not fold into nonsense. The future welcomes exploration because it preserves coherence. The past resists interference because coherence depends on it. This asymmetry is not a flaw in the laws of physics. It is one of their most elegant features. As soon as backward time travel enters the discussion, paradox stops being a playful idea and becomes a serious threat to the foundations of physics. A paradox is not merely something confusing or counterintuitive. It represents a breakdown of logical consistency. Physics depends on the ability to trace a clear chain of cause and effect. An event happens, it produces consequences, and those consequences shape future events. When time loops backward, that chain can close in on itself. An effect can become its own cause. Information can appear without origin. From the standpoint of the equations, this is catastrophic. A universe that allows contradictory histories cannot reliably evolve, predict, or even exist in a stable form. This is why paradox is not tolerated quietly. When the mathematics of space-time is pushed into regimes where backward time travel becomes possible, the equations begin to misbehave. Quantities that should remain finite start to diverge. Energy densities rise without limit. Instead of smooth, predictable evolution, the system explodes into instability. In physics, such behavior is a warning sign. It tells us that we are forcing a model beyond the conditions under which reality can remain coherent. The universe is not being mysterious or philosophical here. It is responding mechanically to a threat against consistency. This reaction becomes even clearer when wormholes are considered. Wormholes are not speculative fantasies. They are legitimate solutions to Einstein's equations. They arise naturally as tunnels through space-time that connect distant regions. In principle, they could also connect different moments in time. This possibility makes wormholes irresistibly tempting as time machines. The mathematics opens the door, but the moment we try to step through it, the universe raises the price dramatically. To function as a time machine, a wormhole must be held open against gravitational collapse. This requires exotic forms of energy that behave in ways opposite to normal matter. While quantum physics allows tiny amounts of such energy to exist briefly, sustaining it on a macroscopic scale pushes us into unknown territory. Even if that hurdle were overcome, a second barrier appears. As soon as a wormhole begins to connect different times, quantum fluctuations near its entrance grow uncontrollably. Radiation accumulates. Thus, geometry becomes violently unstable. Instead of a smooth passage into the past, the wormhole self-destructs. This behavior is not accidental. It is a direct consequence of how quantum fields behave in curved spacetime. Normally, quantum fluctuations are harmless, averaging out over time. Near a time loop, however, these fluctuations reinforce each other. Particles race around the loop again and again, gaining energy with each pass. The result is a runaway effect that tears the structure apart. The universe does not forbid the time machine with a rule. It annihilates it with physics. This is where the idea of chronology protection naturally emerges. The universe appears to defend its own timeline by ensuring that any configuration threatening causality becomes unstable. There is no need for an external enforcer. The laws themselves generate the resistance. When the past is endangered, the environment becomes hostile. Energy spikes, order collapses. The system cannot sustain itself long enough to function as a doorway into earlier time. What makes this especially compelling is that the defense mechanism is universal. It does not depend on human intention or moral judgment. Whether the traveler wants to fix a mistake or satisfy curiosity is irrelevant. The equations respond the same way. The universe protects coherence, not motives. It preserves a consistent history, because without that consistency, reality loses its ability to function. Seen this way, the hostility toward backward time travel is not cruel or arbitrary. It is a form of stability preservation. The past is the backbone of the present. Every structure that exists now depends on a vast network of prior events remaining fixed. To destabilize that network would be to destabilize everything built upon it. The universe reacts not because it dislikes the idea of going back in time, but because it cannot survive the consequences of allowing it freely. This realization reframes the mystery. The universe is not saying that time travel to the past is unthinkable. It is saying that time travel without contradiction is extraordinarily constrained. Any path that threatens logical consistency triggers forces that shut it down. Paradox is not just a puzzle, it is a signal that the universe is approaching a state it cannot maintain. As the picture sharpens, it becomes clear that the universe does not merely stumble when backward time travel is attempted, it actively responds. This response is so consistent across different models that it suggests something deeper than coincidence. Whenever space-time configurations begin to resemble a pathway into the past, a cascade of physical effects emerges that destabilizes the system. Quantum fields fluctuate more violently. Energy densities climb toward infinity. The smooth geometry of space-time fractures into chaos. This behavior points toward a powerful idea that the universe may possess a built-in mechanism to preserve the order of time itself. This mechanism does not look like a rule written into the equations as a simple prohibition. Instead, it looks like a natural consequence of how gravity and quantum mechanics interact. When these two pillars of modern physics are forced into situations where causality is threatened, their interaction becomes destructive rather than cooperative. The same quantum fluctuations that quietly fill empty space suddenly become amplified. Virtual particles, which normally appear and disappear harmlessly, begin to accumulate energy as they circulate through time loops. The result is not subtle. It is catastrophic. The structure attempting to enable backward time travel collapses under its own instability. This is why the idea of the universe defending its timeline is not mystical but mechanical. The laws of physics are not choosing sides, they are enforcing consistency. A timeline that allows contradictions cannot remain stable. Prediction becomes impossible. Memory loses meaning. Cause and effect blur into nonsense. The universe responds to this threat the only way it knows how, by making such configurations physically unsustainable. The closer one gets to violating causality, the more violently the system reacts. What is remarkable is that this defense appears to be universal. It does not depend on scale, intention, or technology. Whether the attempt involves a wormhole, a rotating universe, or some exotic space-time geometry, the pattern repeats itself. Instability grows. Energy diverges. The system fails. This consistency strongly suggests that preserving temporal order is not an accident of specific models, but a fundamental requirement for a functioning universe. At this point, time begins to look less like a passive dimension and more like a deeply protected structure. The universe tolerates extraordinary distortions of space and time as long as they do not undermine coherence. It allows clocks to tick at different rates, observers to age differently, and futures to diverge. But when the integrity of the past is threatened, tolerance disappears. The reaction is swift and unforgiving, not because the universe is hostile, but because stability demands it. Closely tied to this is the role of information. Modern physics has revealed that information is not abstract or optional. It is physical. It is carried by particles, fields, and correlations. Every interaction leaves an imprint. The past is not stored in one location or one object. It is distributed throughout the universe. To change the past would require altering an immense web of information that spans cosmic scales. This is not a local operation. It is a global one. This realization transforms the problem entirely. Backward time travel is not just about moving a person or an object into an earlier era. It is about interacting with an informational structure that has already been written into the fabric of reality. Every atom in your body, every photon traveling through space, every field vibrating in, the vacuum carries traces of what has already happened. The past is reinforced everywhere at once. Trying to change it is like trying to edit every copy of a book that has already been printed, translated, and scattered across the universe simultaneously. Information has a stubborn quality. Once created and spread, it resists erasure. Physics reflects this through conservation laws and entropy. While information can be transformed, scrambled, or hidden, completely undoing it is extraordinarily difficult. The past represents the maximum accumulation of this information. It is dense, interconnected, and stable. The future, by contrast, is information poor. It has not yet been written. This asymmetry explains why physics treats the two directions of time so differently. When you move into the future, you are not fighting information, you are creating it. New interactions occur, new correlations form. The universe welcomes this because it aligns with its natural evolution. When you attempt to move into the past, you are threatening to override information that already exists everywhere. This is not merely hard. It is structurally opposed by the way reality stores and preserves its history. Seen through this lens, the universe's resistance to backward time travel becomes almost inevitable. A stable universe requires a stable past. Without it, learning, evolution, and identity collapse. Memory becomes unreliable. Prediction becomes meaningless. The laws of physics, which rely on continuity and consistency, lose their foundation. The universe does not merely prefer a fixed past, it depends on it. This is why every serious attempt to push physics toward backward time travel encounters the same barriers. Instability, divergence, and breakdown are not obstacles to be engineered away. They are signals that a fundamental boundary is being approached. The universe is not hiding a secret door to the past. It is preserving the conditions that make reality intelligible at all. This way, the resistance to backward time travel is not a limitation of imagination or technology. It is a reflection of how deeply information, causality, and stability are woven together. Time is not just something that flows. It is something that holds the universe together. When quantum mechanics fully enters the discussion, the story of time changes in a subtle but profound way. Classical physics tries to preserve a single, continuous history of the universe, but quantum theory quietly undermines that assumption. At the smallest scales, reality does not commit to one outcome until interaction forces it to do so. Instead, it explores many possibilities at once. Particles exist in superpositions. Events unfold as probabilities rather than certainties. This means that the universe is not built on a single, rigid timeline, but on a vast landscape of potential histories. When this idea is applied to time travel, something remarkable happens. Paradox is no longer inevitable. In a quantum framework, traveling into the past does not necessarily mean invading and rewriting your own history. Instead, the act of interaction can cause reality to branch. The moment a traveler arrives and influences events, the universe may simply follow a different path. The original sequence of events remains intact, while a new history unfolds alongside it. From the perspective of physics, this is an elegant solution. No contradiction arises because no single timeline is forced to contain mutually exclusive events. Cause and effect remain intact within each branch. Logic survives not by forbidding action, but by redirecting it. What makes this idea especially powerful is that it does not feel artificially imposed to save the theory. It grows naturally out of the mathematics of quantum mechanics, the same principles that explain why particles can interfere with themselves and why outcomes are probabilistic also explain how histories might diverge without conflict. Time travel, in this sense, becomes less about changing the past and more about navigating the enormous space of possible realities that already exist within the laws of physics. Yet even here, the universe remains cautious. Quantum branching does not make backward time travel easy or accessible, creating conditions where macroscopic objects can exploit quantum superposition. And branching requires extraordinary control over matter and energy. Decoherence, the process by which quantum systems lose their delicate superpositions, acts as a powerful stabilizer of reality. Large objects, warm environments, and complex interactions all work to suppress quantum behavior at human scales. This means that while branching histories may be allowed in principle, accessing them deliberately is staggeringly difficult. Once again, we see the same pattern. Physics does not slam the door shut, but it places the handle far beyond our reach. The universe allows consistency-preserving solutions, but only under conditions so extreme that they lie far beyond current technology. Possibility exists, but convenience does not. The laws are permissive in theory and unforgiving in practice. This leads to a deeper insight about what time actually represents. Time is not just a parameter that labels events. It is the organizing principle that allows the universe to accumulate structure. The past is the archive of everything that has been learned, built, and stabilized. The future is the space in which new structure can form. This asymmetry is essential. Without a fixed past, complexity cannot build reliably. Without an open future, creativity and evolution stall. The laws of physics reflect this balance with extraordinary precision. Seen from this perspective, the universe's resistance to backward time travel is not a flaw or a limitation. It is a feature that makes existence possible. A reality where the past could be freely rewritten would be unstable, unpredictable, and incoherent. Memory would lose meaning. Identity would dissolve. Scientific laws themselves would become unreliable because their validity depends on a consistent history of cause and effect. The universe protects the past not out of conservatism, but out of necessity. At the same time, the openness of the future reveals something hopeful. The universe is not a closed script, it is a process. It allows novelty, divergence, and exploration. You may not be able to undo what has already happened, but you are free to influence what has not yet been written. Physics does not trap us in regret. It propels us forward into possibility. The arrow of time points not toward punishment, but toward creation. When all of this is taken together, a quiet message emerges from the equations. Time is not merely something that happens to us. It is something that enables meaning. The past must remain stable so that the present can make sense. The future must remain open so that progress can occur. The universe enforces this balance not with intention, but with law. In doing so, it reveals a structure that is both restrictive and liberating, firm in its foundations and generous in its horizons. When we step back from the equations and look at the deeper pattern that emerges, a clear message reveals itself. The universe is not indifferent to time, nor is it hostile to curiosity. It is precise. It allows extraordinary freedoms clocks that run at different speeds, futures that unfold at different rates, and realities that branch under the rules of quantum mechanics. Yet it draws a firm boundary around the past, not out of cruelty, but out of necessity. A stable past is the foundation upon which memory, identity, learning, and progress are built. Without it, reality would collapse into contradiction and chaos. Science shows us that moving forward in time is part of the universe. Its natural rhythm, aligned with expansion, entropy, and creation. Trying to move backward threatens the very coherence that allows the universe to exist in an intelligible form. The resistance we encounter is not a denial of wonder, but a protection of meaning. The laws of physics quietly remind us that while we cannot undo what has already been written, we are not powerless. The future remains open, rich with possibility, shaped by choice, discovery, and understanding. Thank you for watching. And thank you for taking this journey into the deeper logic of time and the universe.